Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Scott Gaudi, who is a professor of astronomy at Ohio State University. His research focuses on developing and applying ways of searching for planets around other stars, and he has been involved with the discovery of nearly 24 extrasolar planets to date. Welcome, Scott.
Thank you for having me, Gil.
Sure, yeah, thanks for doing this. So I want to start with strategy report that was an effort by NSF and yourself and a variety of colleagues, in which you say the past decade has delivered remarkable discoveries in the study of exoplanets. Hand in hand with these advances, the theoretical understanding of the myriad of processes that dictate the formation and evolution of planets has matured. Appreciation of the factors that make a planet hospitable to life has grown in sophistication, as has understanding of the biosignatures, the remotely detectable aspects of a planet's atmosphere or surface that reveal the presence of life. So exoplanet hunting is going on for a while. And I guess we have now different techniques, direct observation to transits, to a technique I think you are more interested in, which is micro lensing. So could you give a quick synopsis of the history of exoplanet hunting and sort of the status quo? How many have you found so far?
So, yeah, sure. I'm happy to do that. I won't go all the way back to the prehistory because there were some claimed discoveries of exoplanets that turned out to be false back in sort of the mid of last century. But really, planet hunting began in earnest with in the late 80s with radial velocity or Doppler surveys for exoplanets. And mostly it came about because of advances in the technology, and in particular, the CCD camera, which allowed us to digitally record spectra for stars. And as you know, the Doppler shift method uses the fact that as the planet orbits the star, it actually doesn't orbit the star, it orbits the center of mass. So the star comes towards you and away from you. So the light from the star is Doppler shifted either to the red or to the blue. And by measuring that minuscule little shift, you can actually infer the presence of planets. So
to do that, I guess the planets have to be pretty big, right?
So definitely the Doppler method is most sensitive to planets that are massive and are in short periods because those induce the largest Doppler shifts. Yes. Okay, so really this started in the story kind of starts with Campbell and Walker, who are two Canadian astronomers at the University of British Columbia. They started a technique where so the issue is not just measuring these lines, but actually referencing them to the correct wavelength. And as your spectrograph is generally not stable, so that wavelength solution changes, which you could think it might be due to a planet when it's just the changes in the properties of the instrument, air pressure, temperature, and things like that. So they had the very clever idea of filtering the light through a gas, and then the gas would imprint lines on the spectra, which we know are at rest. And so then you can measure the relative velocities of those spectra. So they chose an interesting gas, which is hydrogen fluoride, which is colorless, odorless, and tasteless, yet is exceptionally poisonous and basically kills upon contact. So the lore is, and I don't know if this is just apocryphal, is that one of them would be in the main room operating the telescope, and the other one would be outside with two gas masks looking through. And if something bad happened, they would run in and put the gas mask on. I don't know if that's true or not, but it's hysterical. So Campbell and Walker surveyed about 50 stars, I believe, and they did find actually some evidence for Doppler variations that could be attributed to planets, but they were very tentative about their result. And in fact, it turns out one of their signals did actually turn out to be due to a planet. But because they were tentative in their interpretation, they aren't really credited as finding the first planets. So that's kind of where things started. And then a few other things happened. Dave Latham found, with the radial velocity method, something that could have been a brown dwarf, so a failed star, but maybe a supermassive planet, also somewhat tentative. And now we sort of think that might be a real planet. And then Wolfson and Frail, using the pulsar timing technique, which is very similar to the Doppler technique. You're looking for now pulsars coming toward you and away from you. But since pulsars are excellent stable clocks, as the pulsar comes towards you, the pulses are compressed, and as it goes away from you, the pulses are expanded. So by measuring the timing changes of the pulsar, you can infer the presence of bodies orbiting the pulsar. And they found two planets orbiting a pulsar. Pulsar, of course, being a dead star, the remnants of a dead star, massive star. And then later found a third planet around that system. And so that they found the first planetary system, not around a star, but around what we call a stellar remnant, which was very exciting. But then,
when was that?
Yeah, go ahead.
Yeah, when was that?
That was 1993.
1993. Okay,
So
yeah.
Campbell and Walker was 89. Dave Latham was 91. Wilson and Farrell was 93. And this is the really the result that a lot of people know about, and it really kicked off the field of exoplanets, was the discovery of a roughly half Jupiter mass planet orbiting in a period of roughly 4 days around the star 51 Pegasi by Michel Mayor and Didier Queloz. And of course, they won the Nobel Prize last year, sharing it with equally with Jim Peebles for his work in cosmology. So that discovery of 51 Peg really launched the field of exoplanets, and also has kind of threw everything on its head, because we had long had a model for how our solar system formed. And that model predicted that giant planets should only live in the outskirts of the planetary systems, where there's more material to form the cores of the planets, which can then eventually accrete the hydrogen and helium from the protoplanetary disk. But this was a giant planet that somehow had migrated to very close orbit to its parent star. And as I say, like retirees migrating to Florida. And so this really upended people's way of thinking. It was so surprising that a lot of people thought this wasn't a planet. It was due to some sort of stellar pulsations. We now know definitively that these planets, now called hot Jupiters, exist around 1% of all solar-like stars. So and then immediately afterwards, Jeff Marcy and Paul Butler, who were performing a similar kind of survey, radial velocity survey, Doppler survey for planets, they went and looked. They first acquired data on 51 Peg and were able to confirm that that's that Doppler signal and that planet. And then they also looked at data that they had accrued for the past few years and discovered that there were planetary signals in some of those data that they hadn't actually analyzed yet. So then it became this competition between the Swiss group, Didier Queloz and Mayor, Michel Mayor, and then Paul Butler and Jeff Marcy. And so there was this back and forth, and this competition, and at sort of by the end of the 90s, I think there were roughly maybe 40 or 50 planets known by the Doppler method. So that's kind of the first sort of part of the story. The next part of the story is a very important part, and that was when it was discovered that one of these hot Jupiters orbiting the star HD 209458 actually passed in front of its parent star once per period. So its orbital plane was aligned with our line of sight. And so it transited in front of that star. And that enabled you to measure the radius. The Doppler shift allows you to measure the mass of the planet, and therefore you can measure the density. And that conclusively showed that these hot Jupiters were actually gas giants made up of mostly hydrogen and helium. And so that was the final nail on the coffin.
That's a bit like an eclipse, right?
It is exactly like an eclipse, except you're in a very long distance regime.
Right. Right.
And then, so that was the next, I think, big milestone. And this is right about the time when I stopped being able to remember the names of all the known exoplanets. So I started graduate school in 1995, just a few months before 51 Peg B was announced. And so I, along with a sort of generation of other graduate students, grew up with the field of exoplanets. And my thesis was actually one of the first sort of dozen theses on exoplanets. So I'll talk a little bit about what I was working on during this time, but the next big milestone was in 2002. The first planet discovered by the transit method was announced. That was by Kanaki et al. And that sort of opened the door to transit surveys, ground-based transit surveys, finding planets first, and then those being confirmed by the Doppler method. And like I said, that was about the time when I stopped being able to remember the names of all the planets. So the number of transiting
quick question.
Yeah, go ahead.
Scott, so on the Doppler method, I guess this is also, so when you have a system of planets going around a star, all of them have some sort of an effect on the star, right? So how do we sort of precisely figure out what the specific effect is for the star, for the planet that we are trying to determine?
So that's a great question. And in the majority of cases, the signals don't interfere with each other. So they sort of act independently on the radial velocity, the Doppler signal of the star. And so they each have distinct periods, they have distinct amplitudes together, which you can use to estimate the mass of the planet. Now, there are some cases where planets are in what we call resonances, where, for example, every 2 times one of the planets goes around its star, there's another planet that goes around once. Those signals can get much more complicated and are somewhat more difficult to find. And we now know of quite a few such systems that are in that kind of configuration. But by and large, these signals are separable. So just using your regular signal detection techniques will allow you to detect multiple planets.
Okay.
So
transit method,
So the Doppler method had a bunch of success. And then the transit method started having success. And one of the exciting things about transiting planets is you can do lots of great follow-up studies. So sort of mid 2000s when people started doing things like detecting the atmospheres of these transiting giant planets, detecting their thermal emissions so we can measure their temperatures, using things like the Hubble Space Telescope and the Spitzer Space Telescope. And so that's when we really started the epoch of actually being able to characterize in detail the properties of the atmospheres of these planets. Initially the larger ones, but now we're able to do even smaller ones. Yeah.
And so the atmosphere composition through some sort of spectroscopy?
Yes, that's right. So initially it was It wasn't. It was just in a single bandpass, we call it. So it wasn't really spectroscopy, but eventually people were able to use spectroscopy and look for signatures of things like water or methane or things like that in the atmospheres of these planets. And there's been some pretty exciting results with that, and it's getting ever more sophisticated, the kinds of things we can do with these kinds of methods.
So how many have you found so far?
So I think the current count is somewhere around 4,300, which is a lot.
Right.
And the reason why we have so many planets, one of the primary reasons is of course the Kepler Space Telescope. So sort of continuing the thread, there was the first 51 Peg B discovery by Mayor and Queloz, which ignited the field. First transiting planet, HD 219458b. First planet discovered originally by transits. This was in 2002 or 3, I can't remember. Then there was the first discovery of a planet by gravitational microlensing, which is what I work on. That was roughly 2006. And then 2007, I guess it was, the Kepler Space Telescope was launched, which found many thousands of planets and really ushered in the statistical age of exoplanet studies.
And Kepler is using the transit method or something else?
That's right. Kepler uses the transit method. So Kepler, in some senses, was the I mean, it's still there, but it's not operating anymore, was the simplest spacecraft you could imagine. It was just a mirror of about a meter in size, slightly smaller in diameter. It had a very large camera that had lots of CCDs on it, so you could image a large area of the sky. It had I think it had no moving parts other than the reaction wheels, which turned out to be quite critical. And so basically they blew the cover off the telescope and it just pointed at the same place in the sky for nearly 4 years and almost continuously, and looked for these periodic dips as the planet passed in front of the star. And because it's from the space, the precision with which it could measure the brightnesses of the stars was exquisite. That means they could look for very small dips. And that's when we started finding things like things that are smaller than Neptune, with radius smaller than Neptune, all the way down to the radius of the Earth. And even below, I think the record holder is we discovered a planet that has a radius roughly that of Mercury. And Kepler found these planets by, like I said, the thousands. Kepler found multi-planet systems, many multi-planet systems. They found systems of planets orbiting where one planet orbits a binary star. These are circumbinary planets. Lots of exotica that Kepler found, and really helped us to understand what I call the demographics of relatively short period planets with periods less than roughly 100 days.
And micro lensing is a third technique. So,
That's right.
So how exactly does that work?
So it uses the fact that that the mass actually bends light. The gravity bends light, as predicted by Einstein's theory of general relativity. And so what you do is you just stare at a very distant star for long enough. If you do that, eventually another star that's not related to that star, that's in the foreground, will pass very close to your line of sight to that background star that you're monitoring. When that happens, the gravity of that foreground star will actually split the light into two images, which you actually can't really distinguish. We have in actually one case, but we generally can't because they're separated by such a small angle. But the background star itself is actually magnified. So as the foreground star comes into alignment and then goes out of alignment, we see the background star get brighter and then fainter. And this was actually a phenomenon that was predicted by Einstein, I think in 1932, or the paper was published, where he famously said this would never be observed. We've now observed tens of thousands of microlensing events. And the way we use it to find planets is if this foreground star happens to have a planet that has a separation close to where these images pass by the foreground star, then that gravity of that planet, because it has mass and gravity too, will actually also bend the light a little bit and magnify it or demagnify it, but with a much shorter duration. And that's the signal that we use to find planets with microlensing. And because these images are passing at roughly several times the distance of the Earth from the sun from their parent star, microlensing is naturally complementary to the radial velocity and transit method, which are sensitive to short period planets. Microlensing, on the other hand, is sensitive to longer period planets, and in fact, even sensitive to planets not bound to any host star, because those planets have gravity and can create their own microlensing events.
So the foreground star is needed because it's basically bending the oncoming light, and then you're looking for some sort of differential bending on that already bent light.
Right. So, yeah, you see the background star get brighter and fainter, but then for a brief period of time, anywhere between a few hours and a few days, you see a deviation from what you'd expect if that foreground star was by itself. And that signature is you can attribute to the planet, and then you can learn something about the mass ratio and the separation of the planet from its host star.
Okay. And so the 4300 that we found by a variety of techniques, how does the demographics of that look like in terms of size and I guess size is a big part, but also temperature and so on.
Right. So that's a great question, and it's actually a very timely one, because I and my two collaborators, Jesse Christensen, who's been heavily involved in the Kepler analysis of the Kepler data, and Michael Meyer, who's basically works on everything in exoplanets. We just wrote a review on the demographics of exoplanets, and actually there was just a conference last week on the demographics of exoplanets. So this is a hot topic now, because we now have enough planets that we can actually start doing demographics. Right. I think of this as like a survey, a census, whereas you're not doing a deep dive on any individual planetary system, but it's like the 2-page assay of, how many people are in your household, and what are their ages. In this case, what we're typically looking for is the distribution in the plane of the mass of the planet versus its period, or the radius of the planet versus its period. And if you look at the plots like that, you see some interesting things. One is that there's a population of sort of warm or cold Jupiters, with masses between 1 and 10 Jupiter masses, and separations relative to their parent star that are between a few and 5 times the separation of Earth from the sun. You see the population of hot Jupiters that are in periods of a few days and have sizes that are roughly that of Jupiter. Actually, some of them are quite inflated, up to twice the radius of Jupiter, which is still an unsolved problem as to why they're inflated, although there's great theories. And then you see this enormous population of planets discovered by Kepler that have radii somewhere between that of the Earth and that of Neptune, and periods less than 100 days. So these are called super Earths or mini Neptunes. And we now know that these are the most common kind of planet in the galaxy. And what's fascinating is we have absolutely no analog to these kinds of planets in our solar system, both in terms of their size and mass, and in terms of where they're located.
So the warm Jupiter is there is no big puzzle there, right? So 5AU, I guess only puzzle is some of them are really sort of inflated.
The ones in 5AU tend to not be inflated, although we don't have a lot of measurements of radii of those because they're very unlikely to transit. It's the ones that are very close and that are being bombarded by the stellar radiation that are inflated. And somehow that energy is actually being deposited in the planet and causing it to inflate. It's exactly what physical processes is doing that is what is up for debate. The warm Jupiters don't present too much of a problem. We think that they can form in radii that are separations that are slightly larger than that, and then they might migrate in a little bit. The real question that we have is, why in our solar system was there no large-scale migration of the giant planets? We know there was some, and the current popular theory is that Jupiter sort of moved in a little bit and then moved back out. And we know Neptune moved out because it had trapped a bunch of small bodies like Pluto in resonances that I talked about before. The real question is, why is it in some systems we have large-scale dynamical migration and quite chaotic migration, in the sense that you get things with very large eccentricities, and we suspect although we won't know until Gaia tells us, that have large mutual inclinations. And some end up, parked very close to their parent star, whereas our solar system seemed to have a much more quiescent history. And why that is, we don't really know. And that's part of why we do these demographic surveys, is because we think the physics in planet formation and evolution will be imprinted on the final distribution of planets in these parameter spaces that I mentioned.
So I guess the earlier techniques couldn't really discover Earth-sized planets, right? So we have a lot of super Earth-sized planets to the size of Neptune. But with higher sensitivity and better techniques, and now we can measure, or we can potentially discover Earth-like planets too, right?
Earth, I would say we have the potential to discover Earth mass or Earth radius planets. But if you require the Earth-like to be actually at the sort of either separations, or more appropriately, the sort of irradiation levels, the kind of amount of light energy they receive from their parent stars, that region of planet mass, radius, and separation is actually at the sort of nadir of all the detection methods. It's the most difficult kind of planet for us to detect with our current techniques. Which is some sort of cosmic, cosmic joke, if you think about it, right? Is that?
Yeah, that's why I say God has a sense of humor.
Yeah, exactly. So Kepler was designed to actually find exactly Earth analogs, but because, and I mentioned, I alluded to this before, because its reaction wheels failed, two of the reaction wheels failed, it only had two left. It wasn't actually able to point at this location for more than about 3.75 years, where it was planning on pointing at that location for 6 years. And because of that loss of time, it actually didn't quite get to the sensitivity to detect Earth analogs. So our estimate of planets like the Earth orbiting stars like the Sun is based on extrapolation. And this is a famous number called eta Earth. So we have an estimate of it, but it's based on extrapolation. And it's quite important to actually know this number, because if we want to plan future space-based missions, which maybe we'll get to later, that can actually directly image these planets and get spectra of them and look for signatures of habitability and maybe even life, we have to know how common they are.
Right. We'll take a quick break, Scott, and when we come back, we'll talk about exactly that, habitability and what the future plans might be.
All right, sounds great.
Okay. Talk to you soon.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we are back, Scott. We have been talking about exoplanets, extrasolar planets, planets around other stars. And the exoplanet hunting, so to speak, started in the 90s. And different techniques have been used to find them. And over the years, last 30 years or so, we have found 4,300 and counting of exoplanets of variety of sizes, masses, and periods around their stars. And the age-old question of whether any of them is habitable, could be habitable, has life, all those questions still exist and still very interesting to think about. So in one of your papers here, the Habitable Exoplanet Observatory HabEx mission, is that something that is being designed now, or it's already got going?
Neither. It's a wish, I would say. So NASA, every 10 years, the astronomical community self-organizes with the help of the National Academy of Sciences and does what's called a decadal survey. So the most prominent members of the field, they get together, they solicit input from the community, they take that input, filter it, and then they try to determine priorities for NASA, the National Science Foundation, and the Department of Energy for astronomy over the next 10 years. And typically, they often prioritize a large space-based mission for NASA. So, for example, the James Webb Space Telescope was prioritized by one of the decadal surveys, as was the Nancy Grace Roman Space Telescope was prioritized by the 2010 Decadal Survey. We'll get back to that later. And so now we're going through the Astro 2020 Decadal Survey, and it's happening as we speak. The input has mostly been gathered. The sub-panels have mostly written their reports, and now the big main panel, the steering committee, need to assemble all that information and then provide their priorities. In preparation for the 2020 Decadal Survey, NASA basically started 4 studies for large mission concepts that would be submitted to the Decadal Survey and perhaps considered as maybe one of their top priorities. So there's one is the Far Infrared Surveyor, which is now called Origins. The other is the X-ray Surveyor, which is now called Lynx. And then there's 2 missions that are very similar in sort of the science goals, but very different in scope. So one of them is the Large UV Optical Infrared Surveyor, or LUVOIR, which has the dual science goals of, 1, to actually be able to detect and characterize Earth-like planets orbiting the nearest sun-like stars, take their spectra, look for signatures of habitability and life, and also do it in a very wide range of extragalactic and galactic astronomy using a very large aperture telescope. So you can think of this as a super Hubble. So they consider this something that's roughly the size of 15 meters in diameter. So that's much bigger than Hubble. And they also considered a more diminutive 9-meter diameter, which is still, a little less than 5 times that of Hubble. The HabEx, again, had similar science goals, both to try to detect and characterize Earth-like planets around sun-like stars, to look for habitability and life, and also to do a wide range of other kinds of science, galactic, extragalactic, et cetera. But on a smaller scale. So the aperture of HabEx is 4 meters compared to the 2.4 meters of Hubble. Yeah. So it's even actually smaller than JWST, but it's operating at a different wavelength and actually largely complements Hubble. So you can think of it as the next Hubble, whereas you could think of LUVOIR as sort of the big leap after Hubble. These mission concepts were developed over the course of almost 4 years. We submitted our final reports sort of in August of last year. We presented them to the Decadal Survey in the fall of last year. And now we're waiting to see what the Decadal Survey has to say and see if it prioritizes one of these missions as the major mission to go forward in the 2020s. So there are mission concepts that we, I personally hope one of them will be picked. And of course, since I was the co-chair of the HabEx study along with Sarah Seeger at MIT, I'm a little biased towards HabEx.
Yeah. And so this idea that we want to look for Earth-like planets around sun-like stars, we have sort of a defined habitable zone, right? Where water is present. We need rocky planets. So these characteristics are all based on an N of 1 observation.
Right.
Is that the right way to think about it, or could we sort of expand that definition?
So that's an excellent question, and it's one that often comes up in these sorts of things. There's lots of ways to answer that question. Of course, you don't want to restrict yourself to just what you know, right? Yeah. But then again, I like to paraphrase something that my colleague and department chair David Weinberg says. If I asked you to look for a dog, you probably have a pretty good idea of how to go about doing that and what to look for. If I asked you to look for a not dog, that might be a little bit harder, right? We look for what we know. Now, there's actually very good reasons to think that life, if it arises, it might arise on something like the Earth, like you said, a rocky planet with a thin atmosphere, but that can actually, at the right separation, where it can have liquid water on the surface. All life as we know it requires liquid water. Water is very abundant because the two most common elements that like to play with other elements and bond with other elements are hydrogen and oxygen, which is obviously the building blocks of water. And so there's really good reasons to think that this might be the most easy channel for life to arise. Now, we don't know really the habitable zone. We can make educated guesses of what range of separations you can have liquid water, but it depends on your atmospheric composition and lots of other stuff. So the way we look at it in the HABEX mission is that we're looking for something that we know, right?
Yeah.
Let's at least look for test the hypothesis of, are there things like the Earth where we know life can arise? And rather than honing in on just one area, what we really want to do is empirically try to define the habitable zone. So we're going to look at planets not just in the habitable zone, but proximate to the habitable zone, and see if we can define by actually using observations what kind of planets might be habitable and might even have signatures of life. Should we be thinking about other kinds of habitable worlds? Absolutely, and people are. And the astrobiologists are very clever. I think a lot of them worry about false positives, like something where we think we found life, where it's actually some molecule is being formed abiotically and we're fooled. But they also think about other kinds of life, silicon-based life, methane-based solvents, those kinds of things. Yeah. There's a variety of reasons why those kinds of that kind of life doesn't seem as probable. So, for example, methane is only liquid at relatively cold temperatures, at a relatively very narrow range of temperatures, where chemical reactions aren't very quick. If you wanted to build life out of, instead of carbon, silicon does have similar chemical properties of carbon because it's just one row down on the periodic table, but in the same column. But silicon has other things that are bad, like the most common element that silicon would bond with is likely to be oxygen, and it would form silicon dioxide, which of course is sand, and also not very good for making life. So there are good reasons to look for carbon-based life that uses water as a solvent, but of course we should be thinking more broadly than that. So I would say that our approach is to look where we know life can arise, and then if we don't find anything, then we look other places. And of course, concurrently with this, we should be looking for life in our own solar system as well, in Europa, Enceladus, Mars,
which one,
etc.
One of the moons, was it Jupiter or Saturn, has methane in liquid form, right?
So Titan, actually, it's funny.
Yeah.
I just gave a lecture on Titan today to my students, my major astronomy students. Yeah, so Titan is the only other body in the solar system that we know of that has a hydrological cycle. But in the case of Titan, instead of water being the major constituent of the hydrological cycle, it's liquid methane. Yeah. So Titan has liquid methane lakes. And has methane evaporates and it rains, and the whole cycle that like we have on the Earth. So it's actually quite a fascinating world. It's not super promising for habitability, but nevertheless is a very interesting world.
There was something in the news, Scott, I can quite remember, maybe 20 years ago, in a lake in Arizona or someplace like that, somebody thought they found an arsenic-based life. I think that was... that wasn't true. Do you remember that?
I do not remember that. I remember a few sort of false alarms, including the Allen Hills meteorite, although
right, yeah.
Some people still believe that's evidence of past life on Mars. I mean, so science is a process. I think that's people, a lot of people that aren't scientists forget that, and we make mistakes. And the whole reason we do this is that we make hypotheses and make observations, and then someone can go and either confirm those observations or refute them. Yeah. And that's how we move forward. And so an excellent example of this is the possible discovery of phosphine in the atmosphere of Venus. And as you know that it was originally suggested by the authors that the most probable source of this phosphine was life in the upper atmosphere of Venus. And then we're now currently in the process of testing to see if the signal is real, imagining if there's other abiotic ways of forming phosphine. Again, we're moving on. This is how science works. And I don't know how it's going to turn out. It's a fascinating story. I'm not directly involved. I'm just kind of paying attention as a very interested bystander.
So the HabEx mission is important in many ways, right? So your dog and finding a dog or not dog is important because let me ask you this. Suppose you find 100 Earth-like planets around sun-like stars that has all the characteristics, has water, has rocky surface, has been around for a few billion years, let's say, add that to the characteristic, and then we find no life in them, or 100 of them. Wouldn't that, we have to then update our, I would say, enthusiasm for looking out for life, right? I mean, right now, the argument goes something like there are billions of possibilities out there, and it has to be there. But if we don't find 100 of similar environments, that should tell us something different, right?
I think that's right. I should mention, in all fairness, that HabEx actually won't be able to find 100 Earth-like planets based on what we know. LUVOIR might, because it's a much larger aperture and much more capable, and also much more expensive and technologically difficult. These things go hand in hand, obviously. So HabEx is sort of the first step. But even HabEx, if we don't find anything, if we find things that look like they're, for all the world, habitable, they have water vapor, carbon dioxide, Rayleigh scattering indicating an atmosphere, ozone, or sorry, not ozone. Anyway, all those constituents that said, yeah, this looks like a potentially habitable world, but we don't find any oxygen, for example, which is considered a biosignature. And that's true of, all of the planets that we find that are in the proximate to the habitable zone. I think that we would, that tells us something very interesting. I think the argument goes, right, is that life on Earth from geological records basically arose as soon as it possibly could. Right. As soon as they stopped having, basically sterilizing impacts, there's evidence of past life. Now, complex life took a lot longer to form. So the argument, and again, it's a sample size of one, but the argument is that maybe simple life is relatively easy to form. But more complex life is more difficult. But again, it's a sample size of one. And I think it would change our overall perspective, right? So, if we did find that there's lots of potentially habitable planets, but but few, if any, that are actually habitable. And I think these kinds of studies are not just scientific, but they're also philosophical in a way, right? Why do we do this? We kind of want to understand our context and whether or not, we're unique and different, or whether or not there's, abundance of life out there.
Yeah. Like you said, we don't know the answer, but finding either answer, I think, has relevance. And
I think it would be either one would be profound.
Yeah.
If we found life was ubiquitous, that would be very interesting. If we found out that we were cosmically lonely, that would be also very interesting.
Right. Yeah, I want to jump into, you mentioned this, the Nancy Grace Roman Space Telescope. So that's a recent renaming, I guess, of the telescope, right?
So that was originally the Wide Field Infrared Survey Telescope, or WFIRST.
WFIRST, okay. So this is another galactic exoplanet survey, and you're talking here about free-floating planet detection. First of all, so what's the motivation behind free-floating planets to start with?
Right. So first, just a little bit of background. The Nancy Grace Roman Space Telescope is a telescope that's the size of Hubble, but has a much larger field of view, roughly 100 times the field of view. So that means it can map large areas of the sky quickly or smaller areas of the sky, but over and over and over again. And the latter is what we were going to do with it, to use the microlensing method to find what we hope is thousands of planets in the very complementary region of parameter space than Kepler. So we're going to try to fill out this demographic survey and combine it with Kepler to measure the frequency of planets with radii and masses greater than the Earth, and separations from 0 to basically infinity from their parent star, including free-floating planets. Why do we think that free-floating planets might be out there? Well, one is that we have some tentative evidence from ground-based microlensing surveys, which are not as sensitive as Roman will be, but nevertheless have found a population of very short timescale microlensing events that seem like they're probably due to free-floating planets. And in fact, one recent announcement was most likely mass was roughly that of the Earth, which is quite fascinating. Theoretically, there's lots of reasons to believe that free-floating planets, especially low-mass free-floating planets, might be common. I told you before that we know that in a lot of systems, planet formation was very messy. It was chaotic.
Yeah.
The planets moved around a lot. And that process just naturally ejects a lot of small planets. The big planets stay because they have more mass, but they basically kick out a bunch of small planets. This process was almost certainly ubiquitous. And by measuring the frequency of these free-floating planets, especially the low-mass ones, we can get a sense of basically how messy planet formation is in general in the galaxy.
So it could be planets as we know it. It could also be fairly massive asteroid type things too, right?
Yeah, so those would be things that are the mass of asteroids, or even the mass of something like the largest asteroid, like Ceres, or Pluto. Those are going to be very tough to detect, even with Roman. But we think that, so basically planet formation is, it's construction. We think it's a bottom-up kind of scenario. You start with small things, you build bigger things. But just like any construction site, as the building is nearing completion, there's just a bunch of debris all over the place. And that debris eventually just either gets thrown, impacts the planets that are there, or gets ejected from the system. And that's going to be everything from pebbles to asteroid-sized things, maybe even things as big as Mars or Earth. And that's what we would kind of look for. And by measuring the mass function of these things, we can learn something about how the planet formation scenario works, whether most systems were really very messy and threw a bunch of stuff out, or were more quiescent, like we think our solar system formation was.
Yeah, so you say here, so we show that Roman will be sensitive to masses around 0.1 the size of Mars, to gas giants greater than 100 times the size of Mars. So 0.1 mass of Mars, that's a reasonably small body, right?
It's roughly the mass of the moon.
Oh, mass of the moon. Okay.
Yeah.
So we could actually detect something like the moon out there.
Yeah. So one of the great things about microlensing is we could detect things that are roughly twice the mass of the moon. Either bound to their host stars or free floating, although the free floating ones are much harder. They would have to be pretty common for us to detect many of those. But in principle, we could detect systems like the Earth-Moon system. And one interesting thing is that studies from graduate student in Cornell, whose name is escaping me, unfortunately, showed that actually when Earth planets, if you have an Earth-sized planet, mass planet with a moon, and that gets kicked out by, say, a Jupiter, often it'll take its moon with it. So we could imagine free-floating planets with moons, which is actually quite an interesting idea. And we might be able to be sensitive to those with Roman.
So when these things are ejected, I mean, it's obviously a variety of speeds, but do we have an understanding of what speed they might travel?
They're basically ejected at the orbital velocity that they had. So it's they're not ejected with an enormous amount of energy. So that we expect them to have velocity distributions that are basically similar to the stars in our galaxy, maybe a little bit larger. Yeah.
So you are trying to convince the funders that HabEx is a good idea. In conclusion, I want to ask you, Scott. So as you designed this, And you have done a lot of work in the area of exoplanets. You have seen all sorts of different things there, different characteristics. What's your general sense of habitability? If you were to speculate, is it, that I hear from people on both ends of the spectrum. Some say it's a no-brainer that it should be all over the place, and others say that it's so complex. We don't know zero divided by or zero multiplied by infinity what that is.
Right.
It's an undefined thing. So where do you come out on that?
So I'm gonna cheat a little bit and give you two answers.
Yeah.
So before COVID, I used to spend a lot of time on airplanes, um, and and occasionally, this person next to me would try to strike up a conversation, and inevitably, if they did, and I always say, if I feel like talking, if I don't feel like talking, I'll tell them. Eventually, they'll ask me what I do.
Yeah.
If I don't feel like talking, I'll tell them I'm a physicist, and the conversation ends there. If I do feel like talking, I'll tell them I'm an astronomer, and then like 9 times out of 10, their eyes light up.
Yeah.
And inevitably, in the course of the conversation, they ask me, do you think there's life out there?
Right.
Are we alone?
Right.
And my answer as a scientist has to be, I don't know, right? That's what a scientist will tell you. And then, of course, they say, well, yeah. But what do you think? And I answer, I don't know, but I'm trying to find out.
Yeah.
So that's my science. That is my astronomer official science answer.
Right.
If you ask me as a person, not as an astronomer, do I think that there's life out there? I think yes. I think it would be there's just so many opportunities. We know planets. We know there's lots of stars. We know that carbon and water is very common. We know now that planets are just everywhere. Every rock you turn over, there's a planet. And nature is just way more imaginative than we are. And I just can't imagine that we're living in a universe where we are the only planet where not only simple life, but also complex life arose. So that's what I would say as a non-scientist. But especially my official stance as a scientist is, I don't know.
Yeah. So there are 2 questions, life itself and complex life.
Right.
Now, the Fermi paradox and related arguments say that if you reach some level of complexity, some level of technological sophistication, it doesn't take that long to colonize the galaxy. But we don't have evidence of that happening, right? And so,
well, depending on who you ask, right?
Sorry?
So depending on who you ask, there are definitely people that believe that we've been visited by aliens. I am not one of them, but
yeah, that's right. So they might just take a flyby and say, yeah, it's not worth it to go down there.
Especially if they flew by in 2020, they're like, nope, we're just gonna pass this one right by.
That's right. Let the elections get over, and then we might.
Right.
So yeah, I mean, it's an interesting question. Still remains to be why we haven't found anything. Colonization of the galaxy hasn't happened. At the very least, I think we can say that, right?
I think it's pretty clear, and if it has happened, it's happened in a way that has been designed so that primitive civilizations like ours can't actually figure it out. But that I would say that's true. The Fermi paradox is actually troublesome if you really believe that complex life, intelligent life, must have existed. And because there's not a lot of ways out of it. The most promising one that I think of is what's called the Zoo hypothesis, which is kind of like this prime directive in Star Trek, right? Is that we're not going to bother the nascent young civilizations because we don't want to affect their evolution. Right. But it's a real issue. It's a real head scratcher. Why, if it's so easy to colonize once you reach a certain level of technological sophistication, why haven't we seen any evidence of that?
Yeah, I mean, if the standard model holds, then the space-time corridor that we can explore is highly limited, and so yeah. Right. Go ahead.
I mean, it's limited in the sense. Well, so I mean, the crux of the Fermi paradox is that eventually, and so I mean, we've been technologically advanced, if you call us technologically advanced,
Right.
for 100 years or something like that,
That's
which
right.
is a
Yeah.
blink of the eye, right?
Yeah.
If we manage to make it for another 1,000 years, 10,000 years, even 10,000 years is nothing,
Right.
right? But imagine 10,000 years where we might be technologically. Then it's not even now, right now, it's not even that ridiculous to think that we could design a spacecraft that would allow us to get to the nearest planetary system like Proxima Centauri. And then, then it's just a question of developing the civilization there. Each civilization sends out two other colonization probes, and then you start to get into this geometrical argument. And that's the crux of it, is that, 2 times 2 times, 2 to the squared, you start to build up pretty fast.
Right.
The galaxy has been around for sort of 10 billion years. So there've been lots of opportunities for that, and exactly why, it might just be that civilizations just decide that it's not a very good thing to do. It's kind of counter to everything that we know about mankind or humankind.
Right.
We're definitely explorers at heart. But maybe we learn something when we cross some edge of development that we say, actually, it's best to stay at home. Who knows?
Yeah, I mean, that makes a lot of sense to me. So the objective function that we sort of assume may be faulty, right?
Right.
Exploration and acquisition may not be factors in a very highly technologically advanced civilization. Yeah.
Right. I mean, and there's some evidence that this might already be happening, right? I mean, there are lots of arguments now, and that are becoming, and these voices are getting stronger and stronger, that eternal economic growth is neither possible nor a good thing, right? And this is related to things like climate change and things like that. That maybe we want a steady state kind of situation, and maybe that's actually the optimal endpoint of a civilization, is some sort of steady state, and not constantly exploring and constantly manifest destiny taking over other planets.
Right.
Who knows? But one sort of counter argument, that just to close this up, is that at some point in about 4.5 billion years, we had better figure out how to get off this rock, because the sun is just not going to let us live on it anymore, no matter what we do. Yeah. Right. So eventually we're all going to be living around, huddled around little fires of M dwarfs at very, very small separation. Like TRAPPIST-1, that lived for 10 trillion years,
right.
Because all of the sun-like stars will have been long gone by that, after about 1 trillion years. So
yeah, I mean, even tactically, I guess the expectation is that the sun will blow up into a red giant in about 4 billion years.
Right.
About the orbit, the diameter will be the orbit of the Earth. So Earth will be consumed by that. So
there's arguments about whether Earth will actually be consumed or it'll just barely escape. But it doesn't actually matter, because we're going to be burned to a crisp long before that happens. The prediction is that within 2 billion years, we're going to have a runaway greenhouse, and we're going to end up like Venus. So, there are theories that we could just move the orbit of Earth out by exchanging angular momentum with asteroids. Which I think is a very amusing idea. And what I always say is, this is not something you want to sell to the lowest bidder.
CapEx. So CapEx is important from many different perspectives. Yeah.
I think it's just, so I like to say this, but I think it's a little hokey, but it's true. We've reached this very critical point in our civilization, in our technological advancement, in our scientific knowledge, where for the first time in our generation, we might actually be able to go and look for life on other planets, around other stars, within the next 20 or 30 years. It seems inevitable to me, just even despite all of the chaos that's happening in the world and all the other things that we need to do to make sure that humanity actually makes it through this kind of juvenile state that we're in right now, that we will do this, right? I mean, it just, and the cost of it is not that high, right? The cost of HABEX is something like of order an aircraft carrier. So, compared to the defense budget, it's minuscule. Now, There's lots of arguments like we should be spending this on clean water and converting to renewable energy. And I buy all those arguments. But I think as soon as we stop as a civilization seeking knowledge for knowledge's sake, we're on the way down. And so I think that it is both important for humanity to continue on with these kinds of investments, not just in looking for life, but all this pursuit of knowledge in general. And I just think it's a profound question that sort of lingers in everyone's mind. Like I said, almost everyone I know that I meet and they find out an astronomer, they almost always ask me this question: is there a life out there? Are we alone?
Right. Excellent. This has been great, Scott. Thanks so much for spending time with me.
You. All right. Thank you very much.
Thanks. Bye.
Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.